Hey, Harshit, if you've been following this massive growth of AI, you might have likely heard the term of VectorDBs. Companies specializing in this technology like Pinecone have recently received immense amount of funding indicating that this is absolutely the future of data management in AI era. Traditional databases struggle immensely with unstructured data like images, audio, or large text documents because they rely on structured field or manual tags, creating a semantic gap. VectorDBs solve this by turning meaning into maths. In this video, we will cover core concepts of vector embeddings, large and advanced indexing algorithms that make vector search ultra fast, and how they empower the LLMs with retrieval augmented generation with a small practical at the end. A vector database is fundamentally different from a SQL or NoSQL databases we have used for decades. At its heart, it's a database engineered specifically to handle vectors. These vectors are simply fixed length list of numbers that capture the meaning or context of complex objects, whether that's a sentence, an image, or an entire document. Vector databases handle essential database capabilities like data management, CRUD operations, metadata filtering, horizontal scaling, and fault tolerance. However, their specialization lies in their ability to perform similarity searches extremely quickly. Why is this so important? Is because over 80 to 90% of data out there is unstructured, which relational databases cannot easily fit or search conceptually. This specialization makes vector DBs the engine for the current AI revolution. To grasp vector DBs, we first need to understand the core component, the vector embedding. Think of a high dimensional vector like a detailed description of something packed into one long array of numbers. We start with the concept of dimensions. While we easily visualize a 3D space, high dimensional vectors like those used in large language models can have hundreds and thousands of dimensions. Each of these dimensions corresponds to a learned feature of the data. Here's where it gets interesting because the crucial procedure of creating these numerical representations is called an embedding. Machine learning models, such as specialized embedding models like CLIP for images and CLOUD for text, generate these vectors by extracting progressively more abstract features from the raw data. The genius of embeddings is that they capture semantic relationships. Similar words or documents are mapped to vectors that are positioned close to each other in a vector space, and this is called collocation. For example, vectors representing sunset at the beach and sunset on a mountain will share high values for features like strong warm colors, placing them close together, while a picture of a city street would be far away. This mathematical proximity is the basis of a vector search. Vector search leverages the semantic relationships captured by the embeddings. Once your data, be it text, images, audios, is represented as vectors in the database, the search process begins. When you issue a query, that query is also translated into a high dimensional vector using the same embedding model. The database then uses mathematical operations to compare this query vector against all the stored vectors to find the nearest neighbors. How do we define nearest? That's determined by similarity metric. The three most common metrics are cosine similarity, Euclidean distance, and dot product. For example, cosine similarity measures the angle between the two vectors. A value of 1 means that they are pointing in the exact same direction, indicating identical meaning. Dot product similarity is a common choice for normalized vectors, where a high dot product indicates greater similarity. The choice depends on specific use case and data requirements. This system allows for truly semantic search, where you find conceptually similar information even if there are no exact keyword matches. This goes far beyond the limitations of traditional databases. But just generating embeddings is not enough. Think of it like this: if you have millions of books, simply knowing that similar topics are physically close won't help if you have to walk through every aisle to find them. You need a catalog, an index to guide you quickly. For high-dimensional vector data, comparing every vector is simply infeasible due to the sheer volume and complexity. This is why the second key element of a vector DB is indexing process. Indexing maps the vectors into a highly efficient data structure, dramatically reducing computational cost and enhancing accessibility compared to searching raw embeddings. This is achieved using approximate nearest neighbor or ANN algorithms. Unlike the traditional k nearest neighbors, which finds exact nearest neighbors but is slow for massive datasets, ANN trades that minuscule amount of accuracy for a gigantic improvement in search efficiency. This trade off between search accuracy and computational efficiency is crucial for ultra fast performance vector databases deliver in real world scenarios. Let's look at two specific algorithms that are key to vector indexing: HNSW and IVF. HNSW, or Hierarchical Navigable Small World, is one of the top performers in recent benchmarks and is widely recommended. During indexing, HNSW organizes data points into a multi-layered hierarchical graph structure. When querying, the engine quickly navigates this graph, moving between layers from coarse connections to finer details, which strikes a powerful balance between accuracy and speed. You can even tune parameters in HNSW to prioritize latency or recall depending on your application needs. Another popular method is IVF, or inverted file index. IVF works by first partitioning the dataset into several clusters. During a search, the system only needs to check the few clusters closest to the query vector rather than the entire dataset. IVF often works hand in hand with product quantization, a technique that compresses high dimensional vectors into smaller representative codes, further speeding up search, especially in very high dimensional spaces. Understanding these techniques confirm the technical precision required to build and operate high performance vector DBs that excel where traditional systems bottleneck. And as AI adoption has surged, a new problem has also emerged: cost and elasticity. First generation vector databases were fast and accurate, but were often expensive because they required compute instances to run constantly. This led to the rise of serverless vector databases. The core innovation here is the separation of storage from compute. Highly sophisticated geometric partitioning algorithms break the vector index into small queryable subindexes. This means when a query comes in, the system only spins up compute to search the specific partitions needed rather than entire search space. This partitioning is effective but can slow down the initial index build, potentially impacting freshness, the ability to query newly inserted data within seconds. The solution is a freshness layer, which acts as a temporary cache for new vectors. A query router then checks both the main index and the freshness layer, ensuring fast access to most recent data. Finally, serverless architectures tackle multi-tenancy. This intelligently identifies users with similar usage metrics to ensure low latency for everyone without penalizing the cost efficiency of low usage customers. While vector search is phenomenal for semantic understanding, sometimes you still need precision of traditional keyword search. This is why hybrid search is gaining prominence. Hybrid search involves sending a single query that executes both the vector comparison and the keyword comparison in parallel. The strengths of the two approaches are complementary. Vector search finds conceptual similarity in context, while keyword search ensures accuracy for exact matches, which is vital when querying product codes, specific dates, or proper names. The tricky part is merging the two result sets as they rely on different scoring mechanisms. This is handled by an algorithm called reciprocal rank fusion, or RRF. RRF evaluates the rankings from both the vector results and the keyword results, giving more weight to highly ranked items that appear in both lists. The key insight here is that RRF improves the overall quality and reliability of the final ranking. Developers have found that combining these methods significantly boosts search relevance across real-world datasets. The main driver behind the vector database explosion is retrieval augmented generation, or RAG. Large language models, while powerful, have two major limitations. First, they can hallucinate, generating inaccurate information. And second, their training data is static, meaning they lack knowledge of recent events or your private proprietary documents. RAG solves this by using vector database as the LLM's long-term memory. This process is highly effective. First, your documents, say your internal documentation or recent company reports, are converted into embeddings and stored in a vector database. When a user asks a question, the query is used to search the vector DB, which efficiently retrieves the most semantically relevant text chunks. This retrieved text is then automatically added as the context directly into the prompt sent into the LLM. The LLM can generate a response that is grounded in your up-to-date factual information. RAG not only mitigates hallucinations but also allows LLM to use external user-specific data, making them incredibly powerful for enterprise applications. The decision between a traditional DB and a vector DB entirely depends on your use case. The traditional databases excel at handling structured data using SQL to manage data in tables, rows, and columns. They are champions of transaction management, ensuring that data is organized and consistent. And querying in a relational database usually involves looking for exact matches where values precisely equal your query. In contrast, vector DBs represent data points as fixed length vectors, grouping them based on conceptual similarity. Their focus is semantic, finding the closest vectors mathematically. They are crucial for tasks like machine learning, natural language processing, and advanced recommendation algorithms. While RAG is the flashiest use case right now, vector DBs have much more in this AI world. First, they enable true semantic search. Instead of exact keyword match, you can ask the question in natural language and retrieve results based on intent and meaning. Second, vector search is crucial for multimodal similarity search because data like text, image, audio, video all can be converted into vectors using specialized embedding services. You can now search across different media formats using a single query. For example, you could upload a photograph and ask the system to find similar images based on visual features. Finally, recommendation systems rely heavily on vector principles. By calculating the distance between vectors representing user profiles or product characteristics, vector DBs can efficiently identify nearest neighbors, allowing online retailers or streaming services to suggest items highly similar to customers' past preferences. These tools are special because they help computers find similar things, answer complex questions, and understand the hidden context of complex data intuitively. How does complex data end up ready for vector search? Through a process called data hydration. The process starts with your source data, whether it's text, documents, images, or proprietary knowledge. This data is passed through an embedding service, which is essentially a specialized machine learning model. The output is a vector embedding, the list of numbers containing semantic meaning. These vectors are then inserted into your vector DB. It's critical that your vector is stored in some reference or metadata pointing it back to the original content it represents. When the query is performed, the query itself also runs through the same embedding model to generate a query vector. If you use different models for creation and searching, the semantic spaces won't align, leading to inaccurate results. This pipeline ensures that the entire system speaks the same numerical language, enabling accurate similarity search. The vector database landscape is incredibly dynamic currently. We see implementations falling into a key few categories. First are like native vector databases. These are purpose built from ground up to optimize vector storage and indexing. Prominent examples include Pinecone, Milvis, and Chroma. Secondly, we have traditional multimodal databases that have integrated vector search as a core feature. This is a crucial evolution allowing developers to leverage vector capabilities on their existing data stacks. For example, MongoDB's Atlas vector search enables semantic searching across MongoDB's data. Similarly, Postgres users can use PG vector extension to perform efficient similarity searches. Even in-memory stores like Redis Stack offers first-class vector support. Finally, major cloud providers offer numerous options. AWS recommends Amazon's open source service for vector capabilities with Amazon Bedrock, but also supports extension in Aurora and DocumentDB. Azure integrates vector search across Azure's AI Search, Cosmos DB, and Postgres SQL offerings. Landscape is quite competitive, offering developers diverse tools, often utilizing familiar database workloads and existing monitoring playbook. Hey, so I went up and wrote a pretty small code to explain how basic RAG and local LLMs work. So this is something that I made quickly, so it would have some mistakes, and it's kind of not representational of how actual systems work. And it's a just small example of how you can also set up code and start working on something like this. I will upload this in the GitHub that I've built for system design. And what we have basically here is that I'm just importing some dependencies. Currently, it's just some dependencies. Okay, let us think of it in parts, right? So we have this would be the first part. So part one, which is basically I'm loading the embedding model. So this will embed my documents. Then we are initializing the ChromaDB, which is a VectorDB, and then we are creating a collection in ChromaDB. Pretty simple till now. And then this also would come in just part one, which is I'm creating my tokenizer, which is basically my local LLM. So you can run local LLMs. And then we have, okay, then we are just loading this LLM, right? And then think of this as part two. So this is just the initialization part. So init. Then we have this part two, which is documents. So in this, we have these documents, and these documents are contextual or factual information that is not available to LLM while it was being trained. So for example, this Quen model that we have loaded, the 0.6 billion parameter model that we have loaded, it doesn't know what I like. Now I am giving this LLM the information that, okay, I like ice cream, I like mint chocolate chip ice cream, and I like system design. This is something that LLM has no information about, right? So these are my documents. You can make as many documents as you want to, and this can be even dynamically updated, and whatever you want to do it with, you can let your brain run wild on this. And then what we are doing is we are encoding these documents and making them into embeddings. So embedding model.encode documents, what we downloaded here. And then we are just doing, okay, bro, just add these documents into the VectorDB. It is pretty simple and pretty straightforward. And then this is the question. So my question is, what do I like? What does Harsh likes? So without these embeddings and documents, the LLM doesn't quite know what I like. Now after this, it should ideally tell me what I like. And then we just have these query embeddings and just the result. So what we are doing here is, this is my question. I will turn this question also into an embedding, and then I will query the vector database to get the top two results. And now I will just get these top two results, which is my retrieved context from the VectorDB. So those vectors which are the most similar to my given query. And then we have this prompt template. It is pretty simple and pretty straightforward. So answer this question using the provided context. So the context is the top two results from this VectorDB. The information that the LLM didn't have before now goes into its context as a kind of a system prompt and a prompt. And then we have the question that the user is asking, which is basically, what does Harsh like? And then we just ask the LLM, where is that? So yeah, we just ask the LLM, okay, just generate me the response of this, and we get this response. Pretty simple and pretty straightforward. And if we were to run this Python 3.11, you can already see I've tested it all out. It is working. I'll upload this to a GitHub as well. This is just kind of my small demo that I was doing and seeing if I'm able to explain to you in more depth of how things work in local LLM and language and something like that, right? Because what I wanted is everything right now is just run by API keys and all. What I really want you to do is run it on your own device and machine. I have picked models that are small and hopefully will run on your laptop as well. Quen 0.6 billion parameter is a quite small model, but it is still really efficient at answering questions. So okay, I asked him the question, what does Harsh like? It retrieved context that I like ice cream and I like mint chocolate chip ice cream. And then okay, this is just the thought block of the LLM. This is just how it responds. And then we have Harsh likes ice cream, and specifically he enjoys mint chocolate chip ice cream. So that's pretty cute and pretty cute. And if you want to get this example set up, we can just have a glance at this README, where you just need to create this VNV. Now you don't even need to do this since I have made a new requirements.txt because I was having some numpy issues. So you can just install via the requirements.txt. So we can change that. Yeah, I think the auto recommend is correct. And yeah, you can just use it using the requirements.txt, install all the requirements, and then just run it. Pretty simple. And hopefully you can also test it out on your own and play with more RAG and enjoy. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.